All right, so let's begin today's lecture. So, um, last time hold on just a second, I assigned two homework problems. So let's go over these two problems first. Now, the first problem, so I'm going to show you the solution and also I'm trying to explain, okay? So the first solution is that we have a G, it's an open set, and we're trying to show that G has no isolated point. So that's the number three. So the solution is here. So if you look at this for a while, but instead, I explain this solution in detail. I'm trying to explain everything through a picture. All right. Now here's the situation. So I have a open set. Okay, it's an open set. So we're trying to argue by a contradiction. Okay. Now suppose this open set carries a isolated point outside. I mean, the point is not really in exterior of G, but actually is a part of G, except that it's isolated to other point in G. Okay, so that's a picture showing you the situation. Now, by the definition of isolated point, it means that uh, the point is in the exterior. Well, it looks like pointing in the exterior. So what does it mean is that there is a small ball, okay, surrounding this point, so that inside this ball there's no other point from G. So that's what I mean by isolated point. So if an open set carries such an isolated point, and you are going to have a contradiction because every point in an open set is an interior point. So this means that this isolated point is not really isolated. It has to be an interior point. Interior point means that there's a small ball surrounding this point, so that every point inside the ball is going to be inside G. So you can see you have two balls. That's if you take the smaller one, then you can see that smaller ball will contradict to each other because in one side, since it is isolated, so this ball carries no other point from G, and since the point is also interior, so this means that the small ball carries, I mean, every point inside this ball will be a point in G. So these two things are contradict. Okay, so if you put this contradiction together, you can complete the proof. So it's not a difficult problem. So that's number three. Now let's look at number four. Number four is about a cluster point or a point of accumulations. Okay, uh, by the definition, a point is a cluster point. It means that every ball surrounding X carries some point in A, which is different from the X itself. Okay, it carries another point in A. Basically, it is a mean. So here, what we're trying to show that a point is cluster point if only if actually every ball contains infinite many points of A. So this is a big difference. Now, original definition only require additional point from A, but the theorem saying that this is equivalent to that every ball carries infinitely many point of A. There's a big difference, right? But actually, we can prove it. Okay. Now, one direction is easy. Suppose we know that every ball consists of infinite number of points of A. Of course, this will satisfy the requirement for a point to be a cluster point because infinite number of points of A, this you can find the point different from X, right? Now, so difficult part is that from the original definition, we're going to show that every ball will contains actually infinitely in, infinitely many points of A. Okay, so here is the proof, but instead of explain the proof itself, I'm trying to explain everything through a picture. So let's think about this case. So center is a cluster point, okay? Then I take a ball. I choose a ball surrounding at this point. Then based on definition, we know that inside this ball there must be some point okay, additional point from A, which is different from the center. But we're going to show that inside this ball, there's an infinite number of points from A, okay? Now, we use the contradiction method. Just suppose that there is a ball surrounding this X. Actually, inside this ball, there's only a finite number of points like this, only a finite number of points. And we're going to, from here, we're going to show that this actually contradicts to the definition once I choose a smaller ball. Now, since there's an infinite, only a finite number of points, so you can look at the distance, okay, distance from the center. There must be the minimum distance, the shortest distance, right? Okay. Now, if you have an infinite number of points, then this point maybe accumulates or approaching the center, so you cannot find the smallest distance. Now, if you have only a finite number of points, then the smallest distance actually exists. In actually, you can find a small ball, okay, so that the radius is smaller than the smallest distance. So in this case, you can see that if we concentrate now on a smaller ball, then inside this small ball, there's no point from A, no other point from A for this small ball. So this will contradict to the original definition. Original definition says every ball should carry some point from A, another point from A. But inside this small ball, there's no other point from A. So that's a contradiction. So you, based on this idea, write down a proof, you'll get things done, right? And that's just what I'm going to review a little bit more is about the theorem we proved last time about BW theorem in RP. So this theorem says that every bounded infinite subset of RP has a cluster point. So this is what we did, okay? And actually from here, we can draw some consequences. Now, the first consequence we're going to draw, or you can think is some examples or extended problems, okay? Like this. And so we know that every bounded infinite set has a cluster point. Now, let's say that A is a cluster point of A, okay? A is a cluster point of A. Then there exists a sequence of points, okay, like the AN, so that the limit of AN goes to A. So that's a natural consequence, okay? So how this is going to be proved? So this is very simple. I mean, if you look at the previous case, and you can see that no matter how small the ball is, okay, no matter how small the ball is, I can always find a sequence, okay? I can always find some point from A, right? So if I shrink the ball, I choose a sequence of ball getting smaller. For each ball, I choose a point. Okay, then this sequence of point will obviously approach to the center. Okay, so that's the idea you can use to prove this result. Okay, so if you combine this with the BW theorem, then you can conclude that every bounded infinite subset of RP has a convergent sequence of points. Okay, as a convergence. So I'm going to show you some picture, okay? So suppose I have an infinite set. Normally, when we have an infinite set, we can demonstrate this infinite set by sequence, for instance, for the simplicity. So let's think about a sequence, or A equal to xn, okay, the sequence. So this sequence is considered, well, assuming the term are not always equal, so this means that it's considered is a infinite set of points, okay, in R1. So we're talking about R1 now. So let's take an example, like say xn equals to -1 to n times n over n plus 1. So basically we have a sequence. Now for the sequence n over n plus 1, so this sequence without the -1 to n, okay, then this sequence is very simple. It goes to 1. Now with -1 to n attached, then this sequence will become oscillated. Oscillated, I mean, basically, in one side it's approached to -1, in other side it's approached to 1, because whenever n is odd integers, the -1 become -1. And if n is an even integer, then -1 to n is disappear. Okay, so in this case, you can see that the sequence split into two ends. So therefore, you can easily see that there's a two points of accumulation, or two cluster points. That's -1 and 1. Okay, and then you can see if you take the n to be 2k, the even index, then this subsequence actually goes to 1. Now, if you take the odd index, then the -1 will be with the sequence. Then the sequence will go to -1. Okay, so this is an important example in showing you that if I give you something like an infinite number of points, a subset, and you should be able to identify what is the associated cluster point. What's the associated cluster point? And for each cluster point, you should be able to find a sequence approach to this cluster point. Okay. The one thing you have to be you notice from the example is that both cluster points are not inside the A itself, so they does not belong to A. Okay, they are in the boundary of A, So think about this sequence. I mean, maybe in your free time you can think about the sequence A equals xn. Well, here I'm showing you the cluster point. Now, besides cluster point, you can talk about like the interior point of A. Now, what is interior point? Does A carries any interior point, or the boundary point? Things like that. Okay, you can think about this, and maybe later I can give you additional review on that. Okay, today we're going to continue on a new concept called a compact set. Now, this is an extremely important concept, okay? So let's first define, now the definition of compact set is complicated, but however, the facts about the compact set are really simple, okay? Now here, let's begin with definition of compact set, okay? Now let's say you have a set K in RP. Now this set K is said to be compact if the following condition hold. Now the condition is a very complicated condition. It says that whenever it is covered in the union of a collection Y equals G alpha of open set. Now what this means is that whenever you use an open set, a group of open set to cover so that the union of this group open set covers the entire set K, okay? Then it is also contained, so the K is also contained in the union of some finite number set in YP, in Y. What does it mean is the original and the original family of open set maybe carries infinite number of open set, or even non-countable open set involved. But however, if the K is compact, then you can always find a finite number of them, just finite number of them to cover the K. Okay, I'll show you a picture of this. So here's the K. Okay, now I have a group of open set covering this. So this means that I have many open set that covers one by one, so that its union covers the K. So that's what I mean by the K is covered by a G alpha. So here I only show you a finite number of G alpha. I can't show you infinite number of G alpha. Maybe in some example. Okay. So what is saying is that no matter in this situation, you can always select only a finite number of those red open set to cover the K. If the K carry this property for every collection, okay, and this is called a compact set. So the collection Y of open set whose union contains K is called covering of K. So sometimes they call it open covering of K, but it doesn't matter. So let's simplify this notion, just saying that it is a covering of K. Okay. So it's a covering of K. So therefore, the requirement that K to be compact is that every covering of Y of K can be replaced by a finite covering of K. The finite covering is a subcovering of the Y, using only set in Y. Okay, so that's the requirement. Now here's some example. Now thinking about the interval minus n to n. So these are open set in R, okay, in the one-dimensional Euclidean space, minus 1 to n. Now, if you collect all these kind of interval from minus 1 n to n, let n varies, then the whole family, the union of all these interval, will cover what? Will cover the R itself. Will covers R itself, right? It's a covering. Okay. Another example is like this. It's an interval from 1 over n. That's on the left end. And the right end point is 1 minus 1 over n. Okay. So this is another family of open sets. And this family of open sets, you can see that it's the whole union is going to cover 0 to 1. 0 to 1. Okay. Now these are the two important covering. And the example, and I'm going to say something about this later. Okay. I see there's a questions. Okay, so there's an internet problems. So anyway, I will continue. So no matter what, I'm going to finish my lecture because I'm recording my lecture. So if you have problems with internet, and then you can view the recorded lecture later. All right. Okay. So this is the important examples, and so what we're trying to do here is that we're going to prove a very important theorem. It's called a Helm-Boreal theorem. So this theorem tells you that even though the compact set is so complicated in definition, but however, actually the compact sets are really simple set. So this theorem says that a subset of Rp, okay, a subset of Rp is compact if only if it is closed and bounded. That's it. So a set to be compact, the condition is that the set has to be a closed set and also a bounded set. All right. So that's the Helm-Boreal theorem. And today we're going to we're trying to prove this theorem. Okay. Prove this. Okay. So but before I prove that, I have indicate the condition here. A compact set has to be closed and bounded. So closedness and the boundedness are very important. Now, if one of these conditions is not attached to here, so the set may not be compact. So I just let you to think about the previous example, interval minus n to n. Okay, so this is covers R, right? Covers the whole space R. And then actually you can see that, so that's a picture. And then you can see that if you only use a finite number of them, then this finite number of them, the union of these finite number of interval cannot cover R. Okay, no matter how large it is, as long as it's finite, then they can only cover a finite number, a finite portion of R, right? So why? So therefore, the R itself is not the compact set. The reason is because obviously it is not bounded. So that's why the boundedness is so important. Okay. Another example is the second one we just studied. Okay, 1 over n to 1 minus 1 over n. Okay, so that's cover 0, 1. And then you can see that even though it's covered, the union, it's covered 0 to 1, but however, okay, no, sorry, and I have been correction. Oh no, that's fine. Then you can see a finite number of them cannot cover 0 and 1 because you can stretch from the left side to the right side, must carry its infinite number n to cover the 0 to 1, from 0 to 1. Only a finite number is only cover a big portion of it. It's never covers the entire region. Okay. The reason why it is because it is not closed. So therefore, from these two examples, you can see that Y, the closeness, it has to be close and has to be bounded in order for a set to be compact. Okay. Okay. So now let's see how we can prove it. Okay. So first, let's prove to prove the if side. So first, let's assume that okay, K is compact. Okay. Then we're going to show that the K is closed. And the idea is that since we're assuming K is compact, so therefore there's a properties associated with compact set, right? So this means that every open covering must carry a finite covering. So the idea is we're going to choose a special covering, and then we can, from this special covering, the result of all this special covering, we'll be able to show that it has to be closed and bounded. Okay. So first things we want to show that it is closed. Now, how do you show something is closed? In order to show something closed, you look outside, right? You want to show on the every exterior point, okay? Every point not belong to A is exterior point. That means you want to choose exterior. The exterior of K is open. Then this will be sufficient to show that K is closed, right? Okay, so let's pick a point. Okay, let's pick a point in not belongs to K. We're going to show that this is an exterior point. Okay, so what we're trying to do is we're going to, for this point, which is not in A, not in K, I'm going to choose a ball, B1/n(x). Now, B1/nx, 1/n is a tiny number. So this means I choose a very small ball, surrounding X. Okay, now here, I didn't specify notation completely. I'm choose a closed ball here. So B1/nx is a closed ball. That means it's include its the boundary. Include its boundary. Okay. Then I look at the complement of this ball. Okay, look at the exterior of this ball. Then the exterior will become open set. Okay, because B1/n is closed, so exterior is open. And so I can, by vary the n, so therefore I can see a family of open sets, which we call Gn, which forms the family Y. So that's a picture. So the point is outside. So you can see I choose a small ball, okay? But the small ball itself is not a Gn. The exterior, now this small ball is supposed to be a closed ball, okay? So the exterior of this small ball forms the Gn. Okay? So you can see that since X is not in K, so therefore you can see that eventually, okay, I mean, as n goes to infinity, 1/n will shrink to 0. So therefore, this ball will shrink just to a single point. So therefore, the union of all these Gn will cover the K. Will cover the K. The only point missed is the X itself. But I know that X is not in the K. So therefore, the exterior of this will cover the K, okay? So you can think about this K, since K is, now we get a covering, open covering of K. Now since K is compact, so therefore there exists a finite number of set in Y, okay? Such that, and it's covered the K itself. Okay, it's covered the K. And so therefore, you can see that then by the compactness, then there exists example on only a finite number of set in Y. So, okay, so that the union of this finite number of set also contains K. So let's denote this finite number of G set to be Gn1, Gn2, all the way to Gnm. Finite number of them, okay? And we can, so therefore K belongs to the union of all these sets. So using the B notation, so K belongs to union of Rp minus of all these small ball. Okay. Now let's assume that so there's only a finite number of set in ball. So let's those index n1, n2. So let's assuming they are in increasing order. Okay. Because they're in the increasing order, then you look at the set, the complement of this small ball. So there will be getting greater and greater. Okay, so the first one contains the second one, then second one contains the third one, eventually contains the last one. Last one carries the smallest ball, so the complement is the largest. Okay, so therefore you can see the union. If you take the union of all these complements, that's just equal to the last one, because all the middle one that belongs to the last one. So if the union is not going to make a big difference of that. Okay, so this means that K belongs to union. This means that K belongs to the complement of the ball with 1 over nm. Okay, so this means that K belongs to that. So this means that X has to be is really a exterior point. Okay, X has to be exterior point because you have a ball surrounding X, which is outside of K. So this means that X is exterior point. So this shows that the complement of K is open. So therefore K is closed. So by choosing this special collection of covering, we can show that actually the K is closed. Now in the same idea, we can show that actually K is bounded. In this case, I'm going to choose a different family of open set. So this time, situation is simpler. I choose Gn is the Bn, okay? Bn, now this time the Bn is, I choose the open ball, okay? And which is open. So this time you can see that as n increase, so the ball getting larger and larger. So I obviously eventually, I mean, the whole union obviously will covers the K. Because n can go to infinity, so actually the whole union actually cover the RP itself, cover the entire space. Of course, it's cover the K, right? Now, since K is compact, so therefore there must be a finite number of them still cover the K. So therefore we run the same game. So let's say that they are the Gn1 up to Gn(m). So the union of this finite number set covers the K, okay? And so this means K belongs to union. Then we may assume that N1, let's say N2 and so on, is an increasing order. So therefore you can see that because increasing order, all these balls getting bigger and bigger, okay? And so therefore the union of all these balls is just equal to the last one, Bnm, okay? So K belongs to the union, meaning that K belongs to the last ball. I mean, the whole ball is contained in some radius, in some ball with a finite radius. So obviously, this means that K is bounded. Okay, so now you can see that I choose two special sequences, or two special family of open sets, open covering. So from there, I can show that K is closed and also bounded. Okay, so K is closed and bounded. These are the necessary condition for K to be compact. Now we're going to show that it is sufficient, and only if part. Okay. Now this proof is actually similar to the previous proof we studied last lecture. So here, so what is the assumption here? The assumption says that we have the set K is a closed and it's a open. It's a bounded and it's a closed set. Okay. And from these two conditions, we're going to show that actually K is a compact set. Now, to show K is a compact set, we have to argue for each covering. I mean, we want to show that for every open covering, and there's a finite subcovering. Okay, so we're going to do this using a contradiction method. Using contradiction method means that we are trying to assume that there is a covering. Okay, suppose there's a covering. Now, first, to demonstrate proof, I can only show this in the R2 case, okay? So let's assume that the K is in R2, which is closed and bounded, okay? It's covered by a family of open set. And let's assume that by contradiction method, assume that K cannot be covered by a finite number of sets in in Y. And then we're going to get trying to get a contradiction. And this proof is a little bit more complicated, so be careful, okay? So we argue about contradiction. Okay. Because now we have two assumptions, so it is bounded and closed, okay? Now, since it is bounded, so obviously I can assume that K is contained in a square closed cell I, okay, with area N. So as picture show that I have a bounded set containing I. It's a big square, okay? And then do the same trick. So I'm going to divide, so I can divide I into 4 equal square, 4 equal smaller cells, closed cell, okay? And then you can see the portion of K in one of them cannot be covered by a finite number of set in Y. Because initially we assume that the K cannot be covered by a finite number of set in Y. So one of them, okay, if you divide this in 4 pieces, then at least one of them cannot be covered by a finite, cannot have a finite covering. Obviously, now if after you divide, each smaller portion can be covered by a finite number of them, then the whole thing can be also covered by a finite number of them, right? So as we assume that at the very beginning it cannot be covered by a finite number of open set, then one of them cannot be covered by a finite number of set. So we denote this cell by I1, okay? Then I continue to divide I1 into 4 equal small closed square cell. Then again, you can see that the portion of K in one of them cannot be covered by a finite number set in Y. And we denote this by I2. So we continue this game over and over. I divide it in this way. So you can get a sequence of nested closed square cell, IN, because IN getting smaller, such that the portion of K in each IN cannot be covered by just a finite number set in Y. Okay, so in this way, you can see that such a sequence IN is nested and satisfy all these conditions. And from there, I'm going to get a contradiction, okay? We also know that the area of IN is N divided by 4N plus 1, and which goes to 0 as N goes to infinity, okay? So by the nested cell theorem, the intersection of IN is not empty, okay? Intersection of IN is not empty. So let's pick a point which in the intersection of IN, okay? So since the portion of K in IN cannot be covered by a finite number of set in Y, so we see that the IN intersect with K is not empty because the intersection with IN is actually cannot be covered by finite number set. So there must be a many point inside. So I just pick a point there. So I pick a point Xn belongs to IN intersect with K. Okay, then we can easily see that the sequence Xn will converge to X because the IN is shrinking. The area of IN goes to 0. And X belongs to each IN. Okay, Xn must goes to X. So you can see that, so what does it mean? So Xn is in K, okay? But Xn approach to X. So what does it mean is that X has to be in the closure of K, maybe on the boundary, maybe interior, I don't know. It has to be in the closure of K, right? But I know that K is closed. So this means that the K has to be equal to its closure. So that's why the point X is inside the K. Okay? Now, I know that the K is covered by that family. So X is a special point in K. So X is covered by some open set in the Y. So this open set is called the G alpha naught, okay? This set covers the K, so covers X. And then since X is, so you can see G alpha naught is open set, and X is a point inside the G alpha naught. So the X is the interior point of G alpha naught. Okay, so therefore you can easily see that when n large enough, okay, the Rn which is containing X must contain in G alpha naught. Okay, so now this is a very delicate detail you have to think about by yourself. Okay, so as n goes to infinity, so Rn shrinking to X, right? And so therefore the Rn will eventually go inside the G alpha naught because X is the interior point of G alpha naught. Okay. Okay, so now let's continue. So this means that Rn, so what does it mean? This means that Rn can be covered by just one open set in Y. Now this is going to be contradict just over one. So the Rn self can be covered by just one open set, right? And therefore the portion of K in Rn can also be covered by just one open set in Y. Now this will be a contradiction because this contradicting to the previous statement that the portion of K in Rn cannot be covered by a finite number set in Y. But here, what we got is that the portion of K in Rn can be covered by just one open set as n large enough. So that will contradict to the original assumption. And this contradiction actually proves the result, proves the theorem. Okay. So this is a kind of a complicated proof, but however, this is a very, very important result in analysis. Okay, we have to use this result in the next chapter or in the any other courses. I mean, high level courses, analysis courses. Okay, extremely important. Okay, so here today is a proof. So the requirement is that you're trying to understand the proof. Okay, and you are not required to reproduce proof by yourself, but you're just trying to understand all the detailed proof. So that is important. Okay, so from here, there's another theorem. It's called a Cantor intersection theorem, and I'm not trying to prove it because we don't have enough time. So I'm going to just state the result. And if you are interested, you can look at the notes by yourself. Okay. If later, if I have extra time, if you are interested, I can present additional lecture on this. Now, what is Cantor intersection theorem? Now, let's recall that the nested cell theorem. Nested cell theorem saying that if you have a closed cell nested, okay, so the intersection will be non-empty. So that's a nested cell theorem. Okay. Now, here, so nested cell theorem involve only cells. Cells are very special set. Okay. Now, this result can be generalized to just the general closed cell, the closed set. That means instead of using the closed cell, now you're thinking about closed set itself, closed set. Okay, then the results still hold. So this is called a Cantor intersection theorem. So this theorem has a very trivial assumption saying that the I1, that means the first set in the sequence, is non-empty, closed bounded set. Okay, so that means like you can see if you consider the closed cell. So this closed cell should satisfy this property. But here, so we replace this closed cell by the closed set. So we are putting some restriction on the first one. That means the F1 has to be non-empty. So if you have empty set, then there's nothing you can talk about it. Okay, and we assume that F1 has to be bounded closed set. Okay, now let's Fn. So starting from F1, you get Fn. So Fn to be a sequence of nested closed set in the sense that F1 contain F2 and contain F3 and so on, shrinking. So you have the picture show you have getting the sequence of closed set which getting smaller. Okay, small. Then the conclusion is that the intersection of Rn is non-empty. So this is called a Cantor intersection theorem. This is the extension of the nested cell theorem. Okay, so I intend not to go over with the probe. So today's lecture, the main purpose is to study the proof of the Hahn-Boreal theorem that's related to the compact set, right? Okay, there's two homework problems associated with today's lecture. Now, first one, you have to show directly that a K defined here is compact set in R. Okay, so now how the K looks like. K is actually given by a sequence, right? The 1 over n is basically, this is a sequence. And this sequence, you can see that carries a limit point, the 0. A 0 cell is not inside the sequence, but if I put the 0 inside the sequence, okay, inside the sequence, and you want to show that this is a compact set. There's a compact set. Now, there's two ways to prove this. One way is to use the definition of compact set. So you have to argue that for every covering, and it can be covered by a finite covering. That's one way. The other way is to use the Hahn-Boreal theorem, okay, to show that K is bounded and closed, and then you can see it is actually it is also compact. Number seven is saying that if K is a compact set in R, okay, we're going to show that K is also compact in R2. Now, what I mean by this? Now, K originally thinking about is a set or a set in R, okay, in the axis, okay. It is compact in R1 sense, and then you can view this K in the plane. It is a set of is a subset of the plane in the subset of R2. Now, if you view K is a subset of R2, it should also be compact. Okay, so that's the questions. And again, so this one can be done by using the easiest way to go. Also, you can do both way, but easiest way to go is use Hahn-Boreal theorem. He's trying to argue with the set is bounded and closed. Okay, in the R2 sense, as long as it is bounded and closed in the R1 sense. Okay, you think about this problem by yourself. And the next time, on Thursday, I'm going to, before we go on to the new material, and we're going to talk about these two theorems. Okay, so this is the ending. This is almost the ending of the chapter 3. So next time we'll begin with chapter 4, and chapter 3 is still require a chapter quiz. So I haven't decided what the time is at. So but anyway, next time on Thursday we'll begin with chapter 4. Okay. Now here we have to be a little bit hurry because we don't have enough time. So to cut some unimportant material. All right. So this is one thing. Now, today, there's another thing I want to do. Another thing I want to ask your help, okay? And I want to do some survey, all right? So here, we are trying to introduce a new class, okay? It's 600 level, and it's called 646. It's called Introduction to Mathematical Data Analysis. The reason of this course is because we are trying to establish a data science track to the BS degree, okay? BS degree. So this class, we're talking about mathematical foundation for the data science, okay? There's no too much prerequisites. I mean, as long as you know some basic calculus, even if the calculus 1 sometimes sufficient, and some basic statistics. But anyway, if you don't have these statistics background, and actually we are going to review statistics a little bit before we touch this concept in the class. Okay, so this is a brand new class, and we're trying to introduce, and I'm expecting this important class for students who want to trying to introduced. Now, the question is whether we want to introduce it this fall or later. So I'm going to do a survey, all right? I'm trying to do a survey, okay? So let me stop this sharing, okay? Now, what I'm trying to do, I'm going to have some pause, okay? I'm going to, how do I do that? Let me see. I have to launch a pause, okay? And you can answer this pause. There's 2 questions. So basically, are you interested in taking this class in the near future? The answer is yes or no, okay? Is this class, if this class is introduced in the coming fall, I mean fall 2021, okay, are you willing to take it? So these 2 questions, you just tell me yes or no. Then I'm going to get this data, all right? So now I'm going to launch the polling, okay? You can answer. Okay, so now launching the poll.
Professor?
Yes.
If we are graduating, how would you like us to answer this poll?
You mean you're graduating this? No, then you don't have to answer. I mean, if you're graduating in the spring, for instance, and there's no time, I mean, you are unable to take this class anymore.
I have another quick question. Would it count as like a category like B or C class in terms of like getting a math major?
No, it's this class is open to any undergraduate student. Well, and if you are getting math major, then this can be one certified one of the requirement.
Okay, thank you.
Yeah. So the requirement C is not going to be updated, but where you are sure that it's going to be, I mean, considered as a one requirement. I mean, satisfy these requirements. Yeah. All right. All right. So I got so that's the result. Okay. It's pretty encouraging. Yeah. Yeah. So yeah, we're in the process now in trying to establish the syllabus and all the teaching material, and most likely we'll be able to. I mean, the thing is, we're still preparing this, so so it's not going to be in the system yet. Okay, in the university system, so eventually will be inside university system, and you'll be able to register for this class. At this time, you can't because it's not ready yet. Okay. Okay, very good. Okay, so thank you very much. So I got this information, and all right. Okay, that's it for today. Thank you.
Thank you.
Thank you. Bye-bye.